A software developer here in Zurich, and also here since 5 years, right?
Yeah.
Also doing Rust since 5 years.
Yeah, in my personal time.
The stage is yours. Thanks.
Thanks for the, yeah, I have my mic. Thanks for the introduction. So today I want to tell you about my journey using SIMD instructions in Rust with Android. And I want to start with a few questions to the audience. Who here has used Rust with Android before? Okay, 2 people. Who has used Rust with Android before? Okay, iOS, one person. And who knows what SIMD means? Okay, around half of the audience. So let's start with this question. What are SIMD instructions? And I'd like to start with going back to the lowest level of abstraction we have at the hardware, which is the CPU, which basically is combined of 2 things: registers, which represent memory, and operations, which are hardwired circuits into the hardware. 2 examples. Here on the left, you have a XOR, which you can imagine is going to have transistors bit by bit to compute the XOR over the whole register. On the right, you have an addition, which conceptually is similar to XOR, but additionally there is some carry bit to propagate throughout the register. So that's the basic block we have. And then with this abstraction of registers and operations, we have assembly code, on top of which programming languages are built as a higher abstraction. So 8-bit is really a very basic CPU. Then over time, CPUs got more and more powerful, so 16 bits, 32 bits, 64 bits. And okay, at some point, nowadays, all modern consumer hardware is 64 bits, so you think, okay, well, did we stop at 64, or what is the issue? And the answer is no. We got wider registers already 20 years ago, but the fact is, okay, what can we do with wider registers of 128 bits? If you think about common operations you do with the registers, for example, pointers to address memory or a loop that you want to iterate through, 64-bit is more than enough for any kind of reasonable computation. So really, it didn't really make sense to use wider registers, which we could build in terms of more powerful CPUs. It didn't make sense to use them all for wide addition or things like that. And this is where the concept of SIMD, which stands for single instruction, multiple data, comes into play. So the idea is to say, okay, we're going to build a wider register, for example, 128 bits, but divide it logically into an array of smaller lanes. So for example, here, 4 lanes of 32 bits. And at the operation level, we're going to take these registers and then, for example, do an addition of 2 arrays, element by element. So conceptually here, you have, again, some XOR happening and some carry bit that will only propagate up to the division of the block. And then there are even more exotic instructions that didn't really exist before, such as shuffling blocks. So for example, you take a wide register, here split it into 8 blocks of 16 bits. You additionally pass a shuffle parameter, and then you have an instruction that will shuffle the blocks and return a register with the blocks mixed together. Another example is a comparison, element by element, where you return zeros in this block if the elements are different, and ones if they are equal. So these are the building blocks that we got from SIMD, and then another question, what can we do with them in terms of algorithms? And why is it faster to use them? The primary example is a loop, and it's called loop vectorization. So you take 2 arrays or slices here in Rust, and you want to add elements of one into the other. element-wise. So you can imagine that without SIMD, essentially you will have one addition instruction for each element in the loop. But with a SIMD instruction that can add 4 of them at once, you can divide by 4 the number of instructions, and so conceptually have the program run 4 times faster. So this gives you a speed up. Another example is, again, the shuffle I presented. If you want to do the shuffle manually, you can imagine that there will be many loads and stores and intermediate registers to use. Here, for example, 8 operations. And with SIMD, you just have all of that in one instruction. So again, you could have a program running 8 times faster with that. And it goes even beyond that. So mostly for cryptographic operations, there are some specialized instructions that will really compute a whole loop in one instruction. So here on the left, you have this example of polynomial multiplication, which, again, it's really a niche application for cryptography, but conceptually, if you want to handle the implementation, you need a lot of XORs and shifts and a whole loop. And here you have just one instruction doing that for you. So yeah, in short, with this building block of SIMD, you have optimized algorithms everywhere. For example, the hash map implementation of Rust is using, since a few years, this Swiss tables algorithm that was published 5 years ago, and that is combining all these building blocks to really speed up the hash implementation. I really encourage you to have a look at how that's implemented. That's really interesting. Other examples would be substring searching or parsing JSON. So all of these applications, go beyond the simple case of vectorizing a loop. You can really leverage these instructions in smarter ways. Any questions about that? All right. So now we want to use them and write algorithms in Rust that use this SIMD instruction. And the first challenge is to, call them from Rust, write a Rust program that uses them. So again, I take the example of an array of 4 elements that I want to add together. So this is the template of my code, and at the bottom I want to write this addition function of 4 times 32-bit integers. So I need to fill this. The first approach is to use inline assembly, which was recently stabilized in Rust. So you need unsafe code for it, but you don't need a nightly compiler. You can use the stable one. So let's try that. Well, the first challenge here, as you can imagine, is you have to find out what is the name of the instruction you want to call. So here, on Intel, for example, adding these two arrays, going through the vendor manual, you figure out that the instruction is this p-add-d instruction in assembly. So once you've found that, you can imagine, let's try to call it like this. And this is where you start kind of fighting the Rust compiler here in terms of syntax for the assembly. So here the first error you encounter is that you cannot directly plug in like arbitrary types into the assembly. It says only integers, floats, SIMD vector types or pointers are accepted. So you need to figure out what to do. Maybe since there are integers, let's try 128-bit ones. And here, I wrote this transmute, so I know that Ralph is going to cry, but it's just to illustrate, don't do this in the real world. Let's just imagine these are 128-bit integers. It still doesn't work because this register class, according to the Rust language, doesn't support wider integers. So then looking a bit more to the Intel's documentation, there is this XMM class of register, and indeed the Rust assembly macro has this class XMM reg. So we're getting somewhere, but still it doesn't support my 128-bit integer. So the next thing is to go back to the nightly compiler and then use this portable SIMD type, I32 times 4, which was recommended by the previous error. And then when we transmute here, okay, this time we get a different error, which is that the first argument needs to be mutable. Indeed, we had the second argument into the first one, so that's easy to fix. We had a mut. And now, okay, we get a weird syntax error. What does this mean? There's tokens and arguments. You know, it's hard to figure out what to do. And eventually, it was just a missing comma between the parameters. So you get the idea, like using this raw assembly, besides being unsafe, is also quite cumbersome to use. And yeah, I also didn't mention there is also these options you can add to the assembly. Pure, no mem, no stack. I mean, you have to read the manual, make sure you uphold all the guarantees and things like that. So it's all very cumbersome. And that's where a new language abstraction comes into play, which is SIMD intrinsics. So the idea is to have functions that will wrap the low-level instructions together with the Rust types. They are defined in the core arch part of the standard library, and the naming is modeled after the respective vendor manuals for Intel or ARM or even other architectures. So let's say if you have a code from C++ that was using SIMD and you want to port it to Rust, you will use the same type of names, if you will. And so yeah, this should be really ergonomic because you just call a normal Rust function. So the way it works is something like this. So here on Intel, again, I have to convert to a vendor-specific type. In this case, is M128I with the underscores. So yeah, again, I'm lazy for the slides. I just transmute. Normally, you have specific functions to call for that. And the addition itself is this nice function. Well, the name is, a bit complicated. It comes from the Intel's intrinsics manual, but you get the idea. You have addition of 32-bit blocks, if you will. You still need an unsafe block for that, but it's much nicer to work with. Any questions on this? So okay, the second part and the second challenge is to write cross-platform algorithms from this. So here I take an example, another instruction. And the question is whether all these names are the same thing or not. Actually, even for each vendor, you have two different names. One is for the intrinsics, and one is a completely different one, is the instruction you would see in assembly. And the answer is yes, these are all the same instructions, but it's hard to know. So in practice, how does it work? Maybe you can try to compare the names. Okay, well, a few bits are matching, but it doesn't say much. Maybe you can check the Rust documentation. So, I mean, there are dozens or even hundreds of intrinsics listed for each architecture. So you have to read all of them. And then, well, even like these two that are similar, that conceptually should do the same thing, in fact, take vendor-specific types, and even the documentation itself is quite different. It's kind of taken from the vendor's manual. So yeah, there are a few keywords that are the same, but it's not so clear. So maybe let's take a look at the vendor manuals. Again, you have like a bunch of pseudocode, and in some cases you need to click through several links, and it's all like, I mean, English text mixed with pseudocode. If you read carefully, you might get an idea that this is what you wanted to do, but it's not obvious. So this is why, if you're going to write code with SIMD, it's really important to test and also benchmark it on real hardware to make sure you did the correct thing you intended to write. Benchmarking is also important because, let's say, not all SIMD instructions have the same costs. Some will take more cycles than others, so it's important to test that. Okay, so now I wanted to test, and well, on Intel I already have my development laptop, but I wanted to test on a ARM, which is the other major platform. And yeah, essentially, either I would buy the most recent Apple laptop, which nowadays is based on ARM, or I just had this old, dusty Android phone, my previous model. I mean, the screen is broken, everything is broken, except it still works. So it's much cheaper and eco-friendly to do that. So yeah, my plan was the following. I wanted to test some SIMD code for ARM. I will compile this code to the Android platform, then make sure that this device actually even supports the SIMD instructions, and then run tests and benchmark.
Could you step 2 steps to the left, please?
Yeah.
Another? Yes.
Hopla.
Thank you.
Yeah, so the next challenge was to use Rust and compile it for Android on user space. So you mentioned a few of you have tried that before, and yeah, it's actually kind of complicated in a way, but the workflow is conceptually the following. If you want to write an Android app and put native code in it, you're going to have a Java source code, which is kind of the main entry point, the main part of your Android app. And then it will invoke native functions into a native language, so in my case, Rust. The Java is compiled to Java bytecode, and the Rust will be compiled into shared libraries for all the CPU architectures that Android supports, which is these 4 ones. And then the whole thing at the bottom is what is packaged into the app. And then at runtime, the specific device you run on will load the native code for the architecture you have. And yeah, how to compile for Android, how to compile Rust for Android in 4 easy steps. There's a lot of steps, so I mean, the most obvious one, you need to install with Rust-up the Linux Android targets. Then you need to install the Android-specific native development kit. And it turns out that depending on the version of your Rust compiler, only certain versions of the NDK will be compatible. So recently the version was bumped, so that's the kind of thing you need to pay attention to. Then you need to configure it somewhere in the Rust as a linker and leave it in your path environment variable. Later you need in your cargo config to configure shared library output. And with all of that, you can compile code. But then the next problem is that there is no standard output. That is to say, you cannot call println out of the box from an Android app because just the Android system will discard std out. So instead, you need to use this JNI crate to call back into Java, and for example, this Android-specific logging class to write, your test thing. So if you just want to do, printf testing, you need to go through all of these steps. And yeah, this is just a quick hello world of how does this look like. From the Rust point of view, you need to define this special unsafe extern function exported as a Java native function, and then call the functions you want. Here I wanted to illustrate, okay, did I even compile for the correct architecture? And Rust gives me with this target arch configuration flag the name of the architecture. So finally I have a hello world, and indeed I'm running on ARM 64-bit. So yeah, wouldn't it be nice if we just run cargo test or cargo bench directly on Android? And the answer is yes. I figured this out afterwards. It's not that complicated, but you need to know how it works. So what happens under the hood when you use cargo test or cargo bench is that, first of all, cargo will compile a test binary, which is the same for tests and benchmark, by the way. And you can get it with this no-run flag. And then, secondly, the tests are invoked, or the benchmarks, and you get a terminal output. And what you can do is register with cargo a special custom runner that will take this test binary as input and do whatever you want it to do. So here, with this Android debug bridge command, we can push the binary directly to the Android device. So it's directly a plain binary. It's not even an Android app, but because Android is a Linux system, fundamentally, you can actually just spawn a shell and directly run code this way. And so that's what I do next. You run the binary with this shell, and you get the output directly in your terminal, which is much more convenient. And yeah, the way it works is you have to register this runner script. You can do whatever you want, and as I explained, what I want is to push the binary and run it. All right. So yeah, after all these steps, I now have Rust code with SIMD running on my Android device, but I still need to detect which instructions are even supported. And yeah, the reason for that is that these SIMD instructions are kind of extensions on top of the CPU architecture. And if you look at the Rust documentation for the intrinsics functions, you will see this yellow notice, which I think is the kind of unsafe guarantees that you have to uphold. That, for example, this specific function is only available on ARM, so that's fine, and only for CPUs that have this Neon and AES features. So yeah, the thing you have to keep in mind is that each CPU model will support its own list of or set of target features on top of the baseline. And if you run unsupported instructions, it will crash the application with illegal instruction, or maybe you get undefined behavior, probably even. you get. So, you know. That's why I took my old device. I didn't want to, crash it. Yeah, so basically you have to make sure that this is that your device supports this instruction, and if it doesn't, you need to fall back to a fallback implementation that doesn't use all the speedups of SIMD. And Rust offers two methods to detect these features on the current CPU. It's documented in this CPU feature detection page. The first one is called static detection, is actually to not detect anything. You just assume it at compile time with this target feature flag. And well, yeah, this will crash your program if run on an unsupported CPU. Otherwise, you can use this macro provided by the Rust language is Arch feature detected. You call this macro at runtime and then validate that you have the correct features. So how does this macro look like? You just pass it a string. The list of strings available is fixed in the compiler, and it returns a Boolean true or false depending on what is available at runtime. So yeah, I run that on my old device, and unfortunately, disappointingly, it only detected 3 features. And yeah, the function I showed before here was required to have Neon and AES as target features, and here I only have Neon, so I was a bit disappointed that I couldn't run my test. So yeah, I just thought, okay, well, what if I run it anyway? Maybe it's UB, maybe it works. Let's at least give it a try. So yeah, I did the following. I just detect that Neon is supported and then call the my nice function here. So here I'm following the template of the Rust documentation about this dynamic feature detection. And so yeah, at the bottom I implement my SIMD specific function, which is unsafe and has this special label about target feature enable equals the features I want to enable. Yeah, and so here I just call the instruction itself to validate that the output bits are the inputs are consistent with the inputs I expected for my test. And I also return a static string just to confirm that this dispatch was to the dynamic function was correct and that I indeed run the SIMD instruction. And turns out that it worked. So yeah, I was really surprised. I was wondering, okay, what is going wrong here? Is the labels put on these intrinsics, are they incorrect? Or is the feature detection not working properly? Yeah, so let's dig a bit deeper. So what happens behind the scene of this is Arch-specific macro feature detected. On Intel, it's very simple. You have a special CPU ID instruction that you can run from anywhere, and it just returns a bit flag. So you can just read these bits and confirm which features your CPU is supporting. On ARM, there is also a special instruction to do that, but unfortunately, it's only allowed to call it from kernel mode. So if you're in the user space, you cannot verify what features are supported, which is a bit disappointing, but that's how it is. So in practice, what happens is that the operating system will implement an API that you can call, and the operating system will call the special instruction for you. And yeah, on Linux, you have 3 methods for that, on Linux for ARM, that are implemented by this std detect crate, which is part of the standard library. Either you call a special function or you read some files from the special proc file system on Linux. So I tried to implement these functions directly myself, and yeah, it turns out that calling these methods was on my device detecting more features than what Rust detected. So it seems that this macro is a bit broken. And yeah, the root cause of the problem was the following. So Android is kind of a Linux-like system, but the macro didn't recognize it as such. So as I mentioned, on ARM, there is OS-specific detection code to run. So there is this dispatch code, and this is based on the target OS string. And the thing is, for Android, the target OS string is set to Android and not to Linux. So here, this block for Linux wasn't called. Instead, there was just a fallback at the end, which basically, as a fallback, was not detecting anything because it cannot do any better. So yeah, that was the root cause of the problem, which led me to my first patch to the Rust compiler. I mean, it's just a few bytes, but I was very happy. And also, thanks for the Rust compiler maintainers, the review was really fast. I don't know, maybe an hour or something to get the first feedback. I mean, I think within a day it was done, you know. And yeah, so with that implemented, I had 4 more features detected. Yeah, I just want to mention about this patch. You know, before sending my patch, I wanted to be confident that it actually works. So I had to build a local Rust compiler to test my patch. Who here in the audience has compiled Rust C before? Okay, like 1/3 of the people. So that's good. And yeah, I mean, in the beginning, I was a bit daunted by this process. I thought, oh, well, Rust C is a big thing and so on. But it turns out that the building guide is actually quite good. Yeah, so I had to run this Python script with setup and build a stage 0 compiler. And then on Android, the NDK is everywhere, including in the compiler itself. So I had to inject that into the config. So again, once you know how to do it, that's good. Otherwise, you can spend some time. And then lastly, I had to build this stage 1 compiler, which, as I understood, is more or less compiling the standard library. So here for all the Android targets this standard library is the code where my patch was. I also needed to compile it for the host target, even though I'm never going to use this local compiler to compile for my host, but that's what was needed. And lastly, I had to add it to Rustup and just run cargo plus and the name of my toolchain build. So yeah, I think I found it also insightful, like that building Rust C doesn't require that many resources. So I did some statistics and experiments about that. In terms of disk, for my setup of just targeting Android, I just needed 10 gigabytes of disk. So If you have even a bigger laptop than mine, you could run everything in RAM, and maybe it's even faster than that. Yeah, but if you have a slower and older laptop with only one CPU and 2 gigabytes of RAM, you can also do it. It's going to take half an hour, but so yeah, that was also interesting to know that compiling Rust itself is accessible for everyone. And yeah, this leads me back to SIMD and the last part of my talk, which is about performance pitfalls. So as I mentioned before, the goal of SIMD instructions is to speed up your algorithms. And so, yeah, when you're going to write an optimized algorithm, you really want to get the best performance. And on top of that, yeah, the promise that Rust intrinsics for SIMD give you is that on the one hand, you will benefit from Rust type checking. You don't have to do all the checks yourself for the assembly. And that at the same time, you would get the best performance without needing to handle the assembly yourself. So I did a small case study here. And yeah, to figure out if SIMD instructions are really a zero-cost abstraction. So the use case here is a bit more complex than just the example from the documentation, which was just about calling a few intrinsics. Here, in the setup, I have a function foo at the top level that will recursively or transitively call intermediate functions, here bar, and then that will itself invoke the intrinsics. So here it's a very simplified example, but let's say, let's say that foo is at the top level my hot path, so I want to inline everything in foo to get the best performance. And also, let's say the logic in foo itself is just calling bar, doesn't depend on SIMD per se, so if I want to write a fallback implementation without SIMD, I don't want to rewrite everything twice. I mean, it might be that there are arithmetic abstractions or whatever. Like in practice, you don't want to rewrite the whole code. And yeah, what happens when I compile this? So yeah, bar was marked as inline always, so that I get this inlining. And here is the output from the compiler explorer. So what is the assembly I got? You can see that the bar function got inlined into foo, but however, all the SIMD intrinsics that I called are separate functions that just basically invoke one SIMD instruction in the middle, but in between there is a lot of boilerplate to jump to a different function, load a value from the stack, then call the instruction, write it back to the stack, and so on. So it seems like there is some overhead going on here. And yeah, when I compile the same code with the Rust flags for the target feature, so at compile time, I guarantee sort of that these features are implemented. Everything got inlined, so I directly have the SIMD instructions one after the other. And therefore, everything was 5 times faster, which is a huge difference. Like 5 times is the order of magnitude you can expect in general for SIMD. So yeah, that was quite a difference. And I think it really highlights this fact that inlining is an essential optimization of a compiler. There was a recent post by Matt Clad I encourage you to read, which was also sort of speaking about SIMD in a way. And yeah, so why were the intrinsics inlined in this case and not in the previous case? So to answer this question, let's take a look at the definition of the intrinsics in the Rust standard library. First of all, you can see that they are annotated as inline, so you expect them to be inlined. But there is also this target feature enabled with the feature name and unsafe. And yeah, the actual implementation is not some assembly, but deferring to LLVM. There is this link name LLVM and a lot of compiler-specific shenanigans, but yeah. So let's focus on the, let's say, wrapper function here. So what happens here? There is this target feature enable equals foo that annotates the function in a special way and says, okay, this function is only available for this CPU feature. And the root of the problem here is that if you have a function with this annotation and another function with different annotations, they cannot be inlined in each other. So I found this few bugs on the compiler about it. Yeah, so I don't know if it's a limitation of the language itself or of LLVM in some way, but yeah, that's something that doesn't happen. And lastly, if at compile time you explicitly enable this target feature, it's as if all the functions in your program were annotated with this feature. So now you can inline them in each other. So yeah, that explains what happened for me. So yeah, in short, if you're going to use SIMD instructions and intrinsics in particular, you have to be mindful of function calls and make sure you annotate your functions. So yeah, like I didn't really find a nice, truly zero-cost abstraction to this problem. You have to kind of choose between various solutions. One is to say, okay, this function is going to be the hot path. I implement everything inside this function. But if your hot path is complicated, it might be not ergonomic to do that. The other option is to rewrite the code twice, with and without SIMD. And here in the SIMD version, you will have to annotate all your functions, okay, with inline always, of course, but also the target feature that you enable, and therefore all the functions have to be unsafe. So we're kind of losing some ergonomics from Rust from that. Another way would be to have the code existing once, but compiling, these hot functions twice with different compilation flags and play with the linker to kind of dispatch both of them. I wrote a post about it, but yeah, it's like a lot more complicated. And the last approach is to use macros to take your input source code, and the macro will output two variants of your code with and without the features. And this is what the multi-version crate is aiming to do. I didn't dig into the details, so I don't know if it works if you call several functions transitively like this. Yeah, so that's it from my talk. Yeah, so just, as a takeaway, the intrinsics for SIMD are not perfect yet in the compiler, but they are still better ergonomics than enrolled assembly. And on top of that, there's this portable SIMD effort to aim to kind of standardize the common functions, the common instructions that are present on kind of all the major architectures, and give also nicer names than the intrinsics I showed before. Yeah, again, big thanks to the Rust compiler maintainers for the blazingly fast code review. And also, yeah, the compiler explorer tool was really nice to see the assembly outputs.
Let's start with offline questions, and then we'll do some online questions. What is the first one? I don't know. One of them.
Have you tried QEMU in ARM64 mode? I think it supports SIMD as well. Would be cheaper than the old Android phone, maybe?
Yeah, so with QEMU, yeah, so there's the approach of taking an emulator, of course. The question is whether the emulator will implement all of the instructions you want to test, including all the most recent ones, whether it will implement them correctly. Hopefully yes, but who knows? And then lastly, there's the benchmarking part, which is important. And I think in practice, for example, I mentioned that the hash map implementation for Rust is now using SIMD. It's not exactly true, because it's the case on Intel where the SIMD implementation is faster. But on ARM, some of the core, let's say, operations that are used in the Intel specific algorithm don't exist in ARM at all. So you have to use other ones, and it turns out that then the algorithm is not faster. So that's the kind of thing, ultimately, if you want to benchmark, you need real hardware as well. And then, here I tried on one specific device, but over time, different CPU models can implement some intrinsics, some instructions faster than the previous generation. So, this you can only get with real hardware.
Any more questions? Otherwise, I can ask internet questions. Let's do him, and then let's do an internet question.
Thanks for the talk. It was great. I was curious, before you submitted the Rust C patch, you were still seeing some features on your Android phone, even though you couldn't call this instruction because you weren't in kernel mode. Where did they come from? Was it just a guess from the compiler? Or?
Yeah, so really good question. I didn't prepare a slide for it, but it turns out that each, let's say, Rust target triple, which is the combination of the OS and the CPU architecture and things like that, can already define some baseline features. So for example, here on Android, the Android docs somewhere says that all the Android devices are required to have this neon feature, which I think is quite common as a baseline for ARM64 nowadays. Maybe not all ARM64 will have that. But anyway, so somewhere in the compiler, the definition of Android for ARM64 will hardcode these features. And so, yeah, the macro here is kind of doing the right thing of not doing any runtime detection if you provide, you guarantee at compile time that the features exist. So either by, it being embedded in the compiler, or if you add this static detection by compiler flags, it will also show up here in the macro, and yeah, the macro will not generate any code. You will just have a true constant replace. So hopefully, then the compiler can also dead code, eliminate the other branch as dead code and things like that.
With the mic. Oh, now we'll do some internet questions. First one is pretty fast. Are there many assembler style that the inline macro supports?
So this one, let me go back to it. So I think, beforehand, this macro was, before it was stable, it was called LLVM ASM. Mm-hmm. Which was using the kind of an LLVM specific syntax. I don't know if it's AT&T or Intel, but nowadays it's kind of a Rust specific one in the sense that, like, the compiler will detect these things like, this print style blocks that X is a register of a certain type and so do some checks. Style. So yeah, there is just one style in this macro. Yeah, I mean. Presumably, you can have assembly in a file and compile it separately and kind of inject it in another way, but I didn't try that at all, so yeah.
Have you looked at other languages like C++ or this Carmon language?
So for now, I just focused on Android, on Rust, sorry. Yeah, I was very interested into how does it work in Rust specifically. Mm-hmm.
All right. Final side note, there is a testing forum for free software from the Free Software Foundation, so I will introduce you to that. Are there any more questions? Otherwise, we'll take a break. Yes, final question.
Yeah, but the device farm, I think, like, there are a bunch of, fundamental crates, like I mentioned the hash map or the string searching or things like that. And I guess, yeah, these kind of crates might be interested into this kind of CI for various platforms because
it's more interactive actually.
Yeah.
You get the shell. It's not CI. You can have CI, that's a different story. So
Yeah, but I guess that would be already a start, because sometimes a maintainer writes a crate for Intel, they don't know anything about other platforms, and then the library doesn't implement SIMD on other platforms, so it's not as blazingly fast as it could be.
In your benchmark, you mainly tested just the intrinsic itself, but did you also think about the difference if you included the feature check macro, how that would affect the performance at runtime?
Yeah, so on the blog posts, I have much more details, but yeah, I also compared on a whole program, what happens if I just do static detection, so at compile time or at runtime, and what was the cost of that. And I think, for me, the idea was that if I was going to put a check for each intrinsics, I'm going to call the runtime check many times, but most importantly, the inlining will not work, so it will worsen performance. And if I put the check at a higher level function, which was kind of the what drove me to this, then there will be fewer checks, and within the checked block, there will be more opportunities for inlining. So it really depends on where you put the check. Otherwise, apart from this inlining problem, the check itself is kind of cheap in the sense that the macro will cache the results into a global variable and only call it once. So if you're in a hot path, in a hot loop, calling the check macro all the time, hopefully your results will be cached in the CPU or maybe in a register. So loading the bit for memory will not be the highest cost. I think it's more the optimization cost of inlining or not that will matter,
Okay,
I think.
thank you.
But